Okay, welcome everybody to the 2021 Nobel Lectures of the University of Twente. On behalf of the Faculty of Science and Technology and Studium Generale, I bid you a hearty welcome. Also the people online who are watching from their computer, welcome. Every year in October, in science world, everybody gets very excited, maybe not so excited yet in Twente. But right after the Nobel Prizes have been awarded, we get very excited here because we try to find speakers, suitable speakers, who can tell us about the prizes and the subject. And this year, I must say it was almost too easy. We found 3 speakers, very good speakers, almost instantaneously. So you can imagine that the prize has not been awarded. You don't know what topic you have to focus on. And this year, we were lucky that we found 3 very nice speakers who can tell us all about this year's Nobel Prizes in physics, chemistry, and medicine and physiology. I think what I can do is, my name is Armagan Kocer. I'm a professor here at the university, and I've been involved in these Nobel Lectures for almost 15 years. So it's really a tradition here at the university, and it's really exciting to have you all here in the audience to listen. First prize that's going to be elucidated on is going to be introduced by Professor Maarten van Aalst. He is actually here at the university. He's a professor at the university at ITC of climate and disaster resilience, he happens to be also director of the Red Cross. Let's see, I have to look at my cheat sheet here. The Red Cross Crescent Climate Center, which is also has everything to do with the effects of climate change. And this year's Nobel Prize in Physics is for the groundbreaking contributions to our understanding of complex systems, and one of those complex systems is our climate, Earth's climate. And the Nobel Prize was awarded to Professor Manabe, Professor Hasselmann, and Professor Parisi for the research in this field. And Professor Maarten van Aalst is going to explain everything about it. Please, the floor is yours.
Thank you very much and welcome. Now, I did study physics, theoretical physics even initially, ended up in astrophysics, then ended up in atmospheric science. So the climate part of what I'll be presenting here is very close to my heart right now. The other pieces are a bit more rusty. So I trust we've got much more up-to-date, up-to-speed physicists in the room to help me out, if anything on the, particularly the theoretical physics part of this Nobel Prize is beyond my current wits. But it is interesting, and maybe also an interesting item for discussion during the Q&A, that the Nobel Prize Committee this year awarded this prize for these complex systems, but with half of it indeed going to the climate problem. Now, when I started studying physics in Utrecht, what is it now? Almost 30 years ago. Wow, that's scary actually. The applied sciences like meteorology and oceanography, astrophysics was slightly higher up the pecking order, geophysics certainly also lower in the pecking order. They were the sort of the mundane types of physics, right? The real, like, powerful physics was general theory of relativity, quantum mechanics, field theory. And that's where the big breakthroughs, you know, connecting gravity and quantum mechanics were to be done by the theoretical physicists. And people were looking down a little bit at the more mundane applied stuff. You know, we figured out all that stuff with statistical mechanics, really nice, we've got it, but now we can apply it. It's up to the technical universities to go and use it. And all that system stuff about understanding what's happening in the weather and so, I mean, it's nice, but it's applied stuff, right? It's not the real hardcore physics. Now, there is really interesting fundamental science to be done still, and I think the fact that the prize was awarded also half to a theoretical physicist is a sign of that. But of course, also these complex systems have proven to be one of the most fruitful but also relevant areas of science in the past couple of decades. So we've made tremendous progress understanding the climate system and making that useful to society, we've also discovered whole new interesting fields where we're connecting the dots in ways that we never have before. So while for a real hardcore theoretical physicist, half this prize might be wasted, I think it's also a recognition for how much interesting physics is actually happening in those connections. And I think that's also an interesting message for a technical university that might see itself as more applied and directed. This is a Nobel Prize that certainly rewards that sort of look at science. So the prize, as already mentioned, went to complex systems in a very generic sense, groundbreaking contributions to our understanding of complex systems. And it went to 3 researchers, but in 2 blocks. And the first part is what I mentioned on the climate. So for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. And that's for Manabe and Hasselmann. I'll come to that in the second half of this introduction. The other part is much more theoretical. That's the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. So this is Professor Parisi, who really developed ways of capturing this in mathematics that turned out to be applicable across many scales. And I'll just illustrate a few of the places where he did this work. He was born in 1948 in Rome, and in the traditional Italian academic way, lived most of his career through the Italian system. Did his PhD in Sapienza, University of Rome, Italy. He's now a professor at that same university still. Made a few connections abroad, but he's one of these classical theoretical physicists that just does his work in one institute, enjoys it there, and makes his contributions from there. Now, as I mentioned already, he has been studying these complex systems, and of course, as any good physicist, you're looking at real systems. You're trying to understand what is really happening in the case of matter, and this is one of those sorts of problems that he was trying to tackle. So if you have loose atoms and you compress, then you can imagine, and from a gas to a liquid to a solid state, you can already see between these two boxes on the right, the pattern is slightly different every time. And what he was trying to express mathematically is whether there's order in that way of how things would then be structured, coming from complete chaos in a way to some sort of structure, because there is structure, things do get packed together, but it's not, every time it's slightly different. So he was working on mathematical representations of such complex systems to understand if you could describe this better. A second example of how he looked at these complex problems was in spin. Think of magnets, for instance, and they want to organize themselves in relation to the others next to them, right? One magnet pointing in one direction and the other one in the opposite direction. Now, if you've got a perfect triangle and you've already got 2 magnets that are nicely aligned, then how should the third one position itself? And there's no perfect answer, right? If he can't relate to the other 2 magnets already on the triangle in the right way. So what happens to that magnet? And of course you can think of that going up in scale and having many of these systems together, but fundamentally there's already that question. And he actually described it very nicely in a lecture at some point about a sort of Shakespearean drama. If you're an individual and you relate to 2 people who don't get along, how do you find your social order in that place? Well, these atoms have the same issue. And an example of that in practice that he studied is spin glass. So that's a metal alloy where, in this case, for instance, you'd have copper with a few iron atoms mixed in. And each of these iron atoms behave as a small magnet, and so they, in a way, start asking themselves this question: how do they organize themselves? And in principle, that is a practical question that you can start studying by just observing, but of course you want a mathematical model that does this in a more universal way. So what he did, and I won't take you through the detailed mathematics now tonight, but he developed a theory of that complexity that describes that ordering in a chaotic system of such somewhat structured, the behavior of those somewhat structured magnetic iron atoms in that spin glass. Now so that worked for this particular problem, but the way he described it, the mathematical tools that he developed, turned out to be much more applicable to many more applications of complex systems. And that is partly why he won the prize. Not just because he was able to understand spin glass, but because he gave us tools to understand and describe that complexity. Now, the second half of the prize went to two gentlemen together. So the way the prize is split, half of it was for this gentleman, Mr. Giorgio Parisi. So he gets half of the prize money. The other half of the prize money is shared between two folks because of their joint contributions to this field. And Professor Manabe is currently at Princeton, but interestingly also, I think again for more applied scientists at a university like Twente, he actually spent quite a lot of his career in much more applied laboratories. So he went from Japan to the United States, so in the same neighborhood in Princeton where he is now at the university. He was at GFDL, which is a lab of NOAA, basically the American KNMI, but of a different scale, of course. But he was basically in the National Weather Service, trying to understand how to model weather and climate to better understand what we could expect happening in the future. So coming back to that original quote in your introduction of all these lectures, physicists try to predict what the future might bring. Well, this is a very classical example of that. And he was in a lab that is quite a fundamental lab, really building models, understanding complexity, but in the end also serving the quest to better predict the weather and the climate. The model that he produced is one that in this time, so the 1960s, you must imagine we now have weather models that run at a tiny scale, you know, a couple of kilometers, all around the Earth. They run multi-model ensembles, and there's giant computers that we couldn't even imagine possible in the 1960s that are constantly running all these equations that simulate our climate system. In the 1960s, the computers were much less powerful. So there wasn't that sort of crude power computational approach to in this case, atmospheric science or climate science yet. What we did have was a couple of equations to understand the basics of how our atmosphere worked. And that is going back to of course, the original notion of just having the Earth floating around in space, being radiated by the sun, right? So you get shortwave radiation coming in that's warming that little ball floating through the universe. That gets a certain temperature, and like a black body, it just radiates long-wave radiation out again. And in principle, you can calculate what the temperature of that little ball should be given the radiation coming in from the sun and at which equilibrium temperature it then radiates out as much as it's getting in from the sun. That temperature turns out to be about minus 18 degrees Celsius. So that would be quite an unlivable planet. So of course we're not at minus 18 degrees Celsius because we have this little atmospheric layer around us. And that acts like a little blanket. That was already understood in the 19th century and certainly in the early 20th century. People realized that there were greenhouse gases around us that were acting as a little blanket around the sun. So we could start to understand also what increasing or decreasing that amount of greenhouse gases might do. And the calculations already done by Arrhenius in 1901 turn out to be remarkably good in terms of, for instance, what a doubling of the amount of CO2 in the atmosphere would do. They calculated at that time 5 or 6 degrees Celsius increase, which is remarkably good if you think of those back-of-the-envelope calculations. But of course, it's not as simple as just a uniform ball circling through space. There's lots of other things going on in the atmosphere. And what Manabe did in the 1960s is create the first models, in this case a one-dimensional model. So he's basically modeling just so you have Earth's surface and then going upwards all the way into space, a one-dimensional model of the atmosphere, where he accounted for, on the one hand, this incoming radiation, and of course with the atmosphere in the middle, of course being absorbed here, heats the Earth, but there's also stuff happening in between. And then infrared radiation, not just going out straight into space, but being absorbed, re-emitted, reabsorbed, etc., in this atmosphere. So that is the radiative transfer piece that Arrhenius already to some extent figured out in 1901. But what they started to add to that is the whole complexity of motion in the atmosphere. And particularly if the Earth's surface warms up, that means that the air at the surface starts warming, that starts expanding, gets lighter, gets lifted up, but of course also brings other gases, including water vapor up. If it's up there, it's colder, and the water vapor condenses into little droplets and releases heat there. So in practice, this whole atmospheric motion, but also the circulation of gases like water vapor, play a big role in energy transfer in that same atmospheric system. And what that one-dimensional model of Manabe did for the first time is to take into account all these different modes of heat transport to try to understand the structure of the atmosphere, and thus how all these energy interactions resulted in the type of temperature patterns that we see in the atmosphere. One thing that he also then showed is that we could pinpoint to carbon dioxide as a key contributor here. And the reason is that if you look at what happens if you increase the amount of carbon dioxide in the atmosphere, so as you know, this is one of the most powerful greenhouse gases that we're concerned about. So one of these gases that absorb the infrared radiation and then re-emit it, but it acts like that blanket around the Earth. What happens is that at the bottom layer, where you're basically below that blanket, you see that the temperature increases as you increase the amount of CO2. If you're higher up in the atmosphere, so here in the stratosphere actually, 20, 30, 40 kilometers altitude, basically the atmosphere is no longer opaque to the radiation going out, but the radiation is mostly radiated out into space. So basically, you can already intuitively feel if you got more atoms at that, or molecules at that altitude, able to radiate out at a certain temperature, you lose more energy out. So basically what you see is a temperature structure where higher up the temperature is cooling and lower down it's warming the atmosphere. So that was predicted by these models and indeed turns out to be happening in the atmosphere. I will come back to that very briefly later, after talking about Klaus Hasselmann's contributions. So I actually met him in Hamburg when I was doing my own PhD at the Max Planck Institute in Mainz and University of Utrecht here. I was doing upper atmosphere chemistry modeling, but we were using the models that originated from his group in Hamburg. And the Max Planck Institute for Meteorology in Hamburg is one of the famous groups where these big climate models that we still rely on to make these predictions also of the IPCC, for instance, that everyone's discussing now towards Glasgow, where they're produced. Those models are by now three-dimensional models, so we're no longer looking just in one category, but we're really modeling the whole Earth system with all the different dimensions and timescales interlinked. So one of the challenges here, and this is one of these elements of complexity, is of course that we know we cannot predict the weather out further than, say, 2 weeks' time. That's really the maximum, because the system is really inherently chaotic, and a tiny difference in initial conditions means you end up with a completely different weather. The famous butterfly in Brazil that causes a storm in Texas. So tiny differences in the initial state have a big impact on later on, but the statistics of how this play out over time are something that you can study and understand. And that is where Hasselmann's work made a major contribution. And one of the things that he then started studying with those models that had all that complexity intertwined is what can we say about what is happening between the different factors playing into the atmosphere system. So we know there's all kinds of forcings. So there's the continuous processes of interactions that I described from Manabe's model already: radiation, atmospheric dynamics, water vapor, and heat transfer with that. All kinds of processes like that, increasing understanding of what clouds are doing in that process, all these things. You can imagine lots of complexity that you can model, and you can work on all these little pieces and plug them in these bigger models. But at some point you want to understand, with all of that, can we now understand what's happening to that big atmosphere system? And of course, one thing is that we have these observations. That's always what you start with. That's the black curve here. And now what they increasingly could do with these models is inject in these models other types of perturbations. So we have the CO2 perturbation that we know is going on in the background. But also, for instance, we have volcanic perturbations. So these are all volcanic eruptions: Agung, El Chichon, Pinatubo. And what you see in the observations is that typically at the time of these big volcanic eruptions, you do see a drop in global temperature. So you actually do see the impact of these disturbances, but also with just that signal, in this case, these are the calculations that show only the effect of natural sources on the atmosphere, such as volcanic eruptions, but also solar variability, you would get the blue line. And this orange line is the one where we also have the CO2 included. And you can see there is, of course, variability in that system, so we're not yet perfectly modeling that system, but we are capturing what has typically happened over the last 150 years. And this work has built our confidence that we're able to understand these different factors playing into the atmosphere, but also that we really have that super high certainty by now that that human factor is a critical one. And by now, this is from the latest IPCC report, so this is no longer Hasselmann's work, but this is the report that came out in August, the summary of all the scientific knowledge about climate change. This is what's been observed in terms of global warming since 1850. This is how we can now piece it apart between the total human influence made up of well-mixed greenhouse gases and other human drivers. What you see here is aerosols, for instance, cooling the atmosphere actually. Solar and volcanic drivers, net zero effect, but some uncertainty around that, and internal variability, modes of variability, for instance, in the big ocean currents that still play a role. And here it's pieced apart even further. So by now, we have a very detailed set of tools to be able to answer these really important questions that are now of global significance. And again, speaking of the physics wanting to predict out, we can also say, this is again what's happened already, these are the emissions that we've done already. We can say, depending on how much we continue to emit, how much the global temperature rise will be. And in fact, we can now even go a step further, going back to this variability and all the complexity in the system. We're now doing the statistics, and these were two studies I was involved with the past summer, the German flooding and the Canada-US heat wave. We can now pinpoint for these individual extreme events, doing the statistics with these types of models, and we can say how an apparently chaotic event in such a system, how the statistics of that are changing. And again, that is thanks to Manabe and Hasselmann's work, putting it all together. Just wanted to pay tribute to another Nobel Prize winner in that connection. I already mentioned my own PhD was with Paolo Parisi, a former Dutch Nobel Prize winner who passed away last year, unfortunately. His work was actually for another global environmental problem, the ozone layer, that you may recall was one of our biggest environmental concerns in the 1980s. We actually discovered too late that satellite observations had already shown that the ozone hole was appearing since 1979, but we only discovered several years later because it sounded so odd that we'd thrown the satellite observations away because we thought they were measurement errors. Well, folks like Paolo Parisi figured out how that could happen. And interestingly, there's also an interaction between that global cooling at higher altitudes and that ozone layer. So there was very interesting science to be done at the time. He won his prize for the discovery of the ozone layer, which is also one that should give us hope. Because we used similar tools, and my own PhD was using Hasselmann's model with Paolo Parisi's additions to understand these things. In the case of the ozone layer, we have solved that global problem largely. So we have been able to find technological solutions, also thanks to all the technology that is produced in universities like here, to actually see that ozone hole starting to get smaller again. And of course, one of our biggest challenges of this time, of your generation, is to do the same on CO2. It's going to be a lot harder, I can tell you. But I think it should give us hope that science has been at the basis of understanding these two problems and that we've already sorted the first one out. So let's do the same with the second. Thank you.
Thank you very much. That was very nice. I think there must be questions. So if you have a question, please let yourself be heard.
The gentleman on the left.
Oh, yes, please. Can you please wait for the microphone?
1 second. Here's a microphone. Go ahead.
Might one expect an influence of the COVID-19 pandemic in view of less carbon dioxide being produced because people worked at home? Is that realistic to expect that, or is that not possible to predict it?
Yeah, so we already studied that. Unfortunately, so the first question is, did that COVID episode, indeed there was a little downturn in economic activity, did that have a measurable impact on global greenhouse gas concentrations? And there was a little bit of a dip in the speed of the increase, is the short answer. So it was still increasing, but slightly less rapidly than it might otherwise have been. That's already a warning sign, right? So we were still adding to greenhouse gases even in that year. The other effect, so that might have led to a slightly less fast warming than otherwise expected, but actually the other effect turned out to be slightly bigger. So if you add it all up, the aerosols that we are also emitting with our economic activity, with our factories and our cars that we're driving and so, cool the atmosphere a little bit. So in the short term, the net effect of stopping all that is that you get the aerosols, which are short-lived, right? So this is not a long-term cooling, but a short-term cooling. Because of the decrease in aerosols, and so the removal of that cooling actually led to a little bit of extra warming in the past year. We already also see that the emission levels are back to where they were. So there was a lot of hope that the downturn in economic activity in general, but also maybe some behavioral changes, like do we really need to fly that much? Do we need to all work in all those offices every single day? That it would change our behavior. Well, sadly, CO2 emissions are rising again like never before, and we're way above the peak that we had before in terms of annual emissions. So I'm not so hopeful that that is saving us. And on the other hand, this is with my Red Cross hat on, we have 100 million people in addition to where we were before in the world in extreme poverty. So we had been declining in extreme poverty over the years. Now we've got 100 million additional people in extreme poverty. So the impacts of the climate crisis are hitting those people much harder than before COVID.
Okay. Are there more questions? Anybody?
What do you guys think? Should the Nobel Prize Committee award a prize just before a climate summit in Glasgow? Is that science getting into the domain of politics, or is that the right thing to do? Who says it's the right thing to do? Mostly yes. Who disagrees? One or two. Do you want to comment why you think it's not a good idea?
Just a second.
I need to think about my answer for a bit. I do think it's a good nomination or a good prize or good subject to give the Nobel Prize to. And I don't believe they have done it on purpose, like so close before the summit. And I think if they have done so, it wouldn't be the best choice to do so. Because what you saw at the last summit, there were a lot of last-minute pushes to change the goals that they were setting in advance. And then at the summit, people or countries try to join those new, how do you say that?
Targets?
The new targets. And then afterwards, nobody reached those targets because they never planned to. And I think it would be foolish to do the same again this time.
But, right. But is there, from a scientific point of view, why now this prize? I mean, I find the results remarkable. I mean, you can clearly see that the model follows the trends that are measured. So to me, I mean, as an experimentalist, I say, wow, that's amazing. But why now? In scientifically then, eh?
Yeah, so scientifically I think there are two moments. So one is, I do suspect, frankly, that there is a little bit of a question like what is most relevant to the world, right? And that was actually also Nobel's original charge for these prizes, right? It's about science making a contribution to the world. So if you ask a question, what is our biggest scientific contribution to the world right now? It's also about what makes a real contribution to what the world needs right now. But that is looking very much at the near-term political cycle. Maybe also you're concerned with the summit in Glasgow, which, by the way, I'm trying to remain optimistic, but I think it's going to be hard. But the more logical timing I would associate with it is this release of the IPCC report last August. So with that report, we actually closed off a couple of chapters where science had gotten to increasing levels of certainty. And we've really entered a new phase where we're no longer basically asking the question anymore even, is the climate really changing? And are human greenhouse gases the main culprit? That station has been passed. That answer has been given by science thanks to these models. And we're now using these models for much more complex questions. So the next stage of the science is really, for instance, these analyses that I showed of the Canadian heat wave or the European floods, where we're able to pinpoint to much more specific events, which in turn, of course, also trigger a different societal debate, right? This is no longer about polar bears in 2100. This is about 200 people dying at our doorstep due to an extreme weather event that has become 9 times more likely.
Getting to specifics, in one of your graphs, you showed the trend indeed, that the models follow the observation, but there was a blip at around 1940. Is that understood? Yeah.
Some of these are understood, but so I'm not 100% sure about. So you mean actually the peak here?
Yeah.
I'm not 100% sure about this particular one. Quite a lot of the bigger variability is differences in the solar cycles, so that might play a role.
Also the measurements themselves, have they been influenced by because they were in a turbulent time? I don't know. I mean,
I don't know the answer. I can look it up for you probably, but this black line is the result of a lot of different observations. It's also not like it's one measurement station where we're looking at this. It's the global observation set using both the physical meteorological stations, but also other sources.
This is also ice cores, for example, or so? Or what?
Yeah, well, for the last 100 years even, the ice cores are not the main source, but it's indeed using all of the sources combined.
Okay.
Yeah,
okay.
And also going back, looking at this is actually a whole art now in climate science, reconstructing. So looking back, for instance, here. There's big gaps right now, for instance, in observations in Asia and Africa. But if you look back for these ages, there are often written records of weather observations from ships or from colonial powers that used to be in these regions that are currently much less well studied, but where we can go back and actually find the data from these places and digitize them now and use them again in these sorts of measurement tracks, but at the much more local scale, so not for the global trends, but for the local ones. And get and improve our models. But anyhow, all of that, if we're unsure about certain regions, even that is factored into how we calculate this black line.
But the main message is that local events, trying to predict what's happening on a local level, is now the sort of holy grail of understanding the climate.
Yeah, partly because
the trends are clear. I mean.
Yeah, so partly because that is frankly what drives public concern a lot more than an abstract global number of 1.5 or 2 degrees of global warming, right? Yeah. Or something that might change over the course of decades. I mean, if it's hitting you now, that's a different story. Secondly, because we're no longer only asking the question, should we be reducing greenhouse gases, or how much can we still afford to emit until things get worse? We're also just asking very practical questions. How do we adapt to what's already changing? So the question is no longer the abstract one is are humans influencing the climate and how is the climate changing? No, I need to know what the climate is so I can adapt my agriculture, or I can design my city differently, or design a different house. So it's become a lot more practical.
Thank you very much. Let's thank Maarten van Aalst once more. We have to move on. There will be maybe afterwards some time to. Let's move on to the next prize, and the prize is going to discuss is the prize in medicine and physiology, by Professor Armagan Kocer, also from our university. She did a PhD in Turkey, in Ankara, also with masters, and then came to the Netherlands and worked first in Groningen and then came to Twente in the chair of bioelectric signaling and engineering. And Professor Kocer is going to explain everything about the prize that was awarded to David Julius and Ardem Patapoutian. Yeah, I don't know if I pronounced it correctly or not. About temperature and sensing receptors in the body.
Thank you very much.
The floor is yours.
Thank you very much. So when we heard about the Nobel Prize this year, my very first PhD student immediately sent a message. He was so happy because the people recognize and appreciate the mechanosensitive ion channels that we were working in bacteria. So today, so the prize goes to somatic sensation, especially how we feel or sense heat and also mechanical forces. So interesting thing is that we as scientists use our 5 senses in our everyday job to solve problems, but we don't know how they work themselves. So it's quite interesting. And here, when you look at the sense of touch, these 2 gentlemen, their work falls into part of touch, but it is more than that. So we will see now what they did. So normally in our skin, so if you see this is the skin, underneath of skin we have lots of sensors. They can sense the heat or the texture of a surface. any pressure. But what happened is that in early times, so we didn't know any of these, of course. So it started first, let me see, in the 17th century, Descartes thought that, okay, we feel the heat from the fire because fire particles are connecting skin to the brain through a thread made by fire particles. So he was thinking like that, which is not too bad. And then in 1880s, there came the finding that, okay, for different parts of the skin, we have different types of sensation. So this was another contribution. And in 1906, Camillo Golgi and Santiago Ramon y Cajal, they got a Nobel Prize because they discovered how the nervous system, including this so-called somatosensory system, they discovered how that works. Or anatomically they described there is such a system that we recognize or sense stuff and goes to brain. And later, Sir Charles Sherrington and Edgar Adrian, they found that neurons are including these somatosensory neurons in the nervous system. So we are getting more and more close to understanding the whole sensing system. And then 1944, Joseph Erlanger and Herbert Spencer Gusser, they differentiated the functions of individual somatosensory neurons. So if you look at this figure, you can see that we have one big neuron, and now you have different parts of it coming to the skin. And these are the sensors, and they are ending up with some parts. And today, so these are the molecules that, or parts of the neurons that will sense the signal and convert it into a form that our nervous system can recognize. So you are, for instance, feeling that something is hot, but that physical feeling is converted into an electrical signal for our brain to understand and integrate and send the signal back. So it means that we have the physical signals in the sensory part converted into electrochemical signals in the brain. And these two gentlemen, David Julius and Ardem Patapoutian, they found finally who are the real sensors in this whole system. So we come from the bigger picture to the final elements that are doing the job. So let's start with David Julius. So he was interested in temperature sensing, and his main question is he likes to understand how do we feel pain. So that is the goal of his work. And to do that, so he thought, okay, when we have very hot pepper, if you eat hot chili pepper, there's a compound called capsaicin which gives that pain sensation. He thought, hey, if I can find the receptor who senses this hotness and gives me pain, maybe I can understand how the pain is sensed in the body. So he said, okay, let me try to find the mechanism of pain starting from hot receptors. What he did, he thought, okay, let's take a neuron which is known to sense capsaicin, this sensing of spicy hot. And what he did is that he removed all the genetic information. And so he said what happens is that the genetic code tells any cell how to make the components, including these receptors. So if you give this all information, some of them will include the information on how to make these receptors that will sense the pain or heat. So he said, okay, let's do this library, all the information put into cells. They are not yet sensitive to capsaicin. They don't know how to sense capsaicin. And he said, okay, if I can now add the pepper, or the capsaicin and see if any of those show an effect, so they start sensing the pain, then you know which gene is giving the recipe, and by expressing that thing, you can find then what the protein is, what the receptor sensing the pain. So that was the setup. So he used these cell line in the laboratory petri dish, and he transfected them. He put the pools of these DNA pool that he isolated from neurons who can sense the pain. And he put them into the cells, and then in one case, he did not put any capsaicin, so they should not sense anything. And in the other case, he put the capsaicin. And if the cell recognizes it, it will give a signal, that green signal. And first, okay, there's nothing in this one. And he used another part of the DNA isolated from the sensing cell. Oh, see, you have now some cells expressing, they have this receptor. And then he moved on. And okay, so he found afterwards, by looking at these cells, he isolated genes, and then find out which gene was responsible for this behavior. And the product of gene is the receptor protein on the cell. So this way, he could find a protein called TRPV1. So this is a transient potential receptor channel 1. So what he did is that, okay, so he expressed that in the neurons, I mean, and then he could see that, okay, now they are, you see the activity of them, they are sensing the pain. But his question was, okay, here they are sensing the capsaicin, but he was interested in sensing the pain. So he said, okay, when the hotness or it is above certain threshold, we feel pain. It's not anymore, if you have a Mexican food with 5 pepper, it's not anymore as maybe tasty as the 2 or 3. So then he said, okay, let's see if they will also respond to, which means that then he was thinking that somehow related that to the temperature sensing. So he said, oh, can I see if they will react to temperature, these capsaicin sensitive receptors? And what he did is that he looked at the activity of cells at different temperatures, and indeed he saw that as soon as he expressed this receptor in the cells, they were activated when you increase the temperature. So he could link then this, he proved initial hypothesis that if that receptor is sensing the capsaicin, that could also sense the temperature. So this is what he showed here. And after him, so this was the experiment at the end. So what he showed is that this is the chemical structure of the capsaicin, what we feel when we eat chili pepper. So these were the cells who do not sense anything. But when he put the DNA of the neuron who can sense the pain, he could identify, okay, this is the molecule responsible for sensing it. And these are ion channels. And if you think about a cell as this room, the ion channel is the door. And so we have how many? So I see here 3 doors, 4 or 5 doors here. So we have 4 or 5 channels in this room. And they all open by different mechanisms. You can do like this, you can slide the door, or you can push it or pull it. In this case, you just need to give the capsaicin that will open the channel, like this, open the door. And then people can go in and out. In this case, they are the ions. After he discovered this very first ion channel, there came many other discoveries on the temperature-sensitive channels, and it turned out that there are different channels responding to different temperatures, so they can open at different temperatures. And on top of that, you can also have receptors that react to cold temperatures. And this was interesting because then both David Julius and the second prize winner, Ardem Patapoutian, they both discovered independent of each other these cold-sensitive channels. And the funny thing here is that the heat-sensitive channel was sensitive to capsaicin, the hot molecule, and the cold-sensitive channel was responsive also to menthol. So when you have a menthol, you feel a little bit cold, right? So then they discovered by using menthol this channel. So you can think of, as a technical university students, or you can think of lots of applications if you are interested in using them. Okay, second one was the Ardem Patapoutian, and he was interested in temperature, but more mechanosensation. How do we sense the tension? And in his hypothesis, he said, well, these sensors has to be on the surface of the cell, and for any sensor to stay on the surface, they should be anchoring themselves to the surface, right? And for that, there are some requirements, one of which is that molecules should have transmembrane regions. And he said, okay, I will first find a cell line that can respond to mechanical stimulation, so he didn't have one yet. And then he said, okay, let's find that one. And he tried different cells, but they did it with a pipette. They pressed the cell to generate a mechanical stimulus, and then they record the electrical signal. So physical stimulus generates electrical signal, and by doing that, they found a cell which is intrinsically sensitive to mechanical response. And he said, okay, then I will look into all the genes in this cell that encodes for proteins with at least 2 of these anchoring structures, transmembranes. And he came up with 72 of them. And then he tried one by one, each of them, into the cells, and touch, and I see which one will work. But hard to believe, but he did all 71 of them, and they all generated current. The very last one was the real one. So then, good that he didn't give up after 70. Okay, so then he found it. So what you do is that you just press the cell and look at the current or electrical signal coming out of the cell. And then by doing that, he looked at which protein it is encoding, and he found, okay, this is a huge membrane protein again, which is called piezo1 and piezo2. And piezo comes from psi, for tension, from Greek. And he was looking for proteins with 2 membrane domains, but this one has how many? 38. So it was an interesting one. Okay, so to wrap up, with their findings, now we know more about how we sense temperature, heat and pain, heat pain actually, touch and proprioception. But they have also other indications, like these ion channels are involved, all these physiological processes as well. And I'd like to finish up with one important message there. So this is how they look like. Once they got the prize, somebody sent lots of hot sauce to him. And he said, no, you should send it to David. It's more relevant, but I'm keeping them, so that's good. And then this is after he learned the news. He was watching with his son the announcements. And what I liked is that for the young scientists, just as he got the Nobel Prize, but he couldn't get the grant again. And then he was quite, it was before that, but then he tweeted also, there is hope that because he did discovery by being successful in another grant. So, thank you very much.
Thank you. Thank you very much. I'm sure there's questions from the audience. Please wait for the microphone now.
Yeah, this question may be a stupid one, but so these sensors which they discovered were like property of the human skin, or is it like throughout the animal kingdom, or?
Yeah, you have mechanical ones and the others in all kingdoms. We studied the bacterial version of them, and you have every living organism has them, and even viruses have, but they don't have the mechanosensitive or temperature, but they have other channels. They also have them, but you have different versions, similar functions, but different channels.
So, but these were specific to humans, right?
Yeah.
More questions? Thank you. I have a question myself. So there's a lot of activity in so-called neuromorphic computing, where people try to mimic in hardware activity or processes in the brain. Is there also such an activity to mimic these kinds of mechanisms, but then in a chip, in hardware? Can you say something about that?
Yeah, there are activities on that, and then because if you compare the neuronal computation to what we are doing now, we are still far away from the natural version of that in the brain. So there are so many parallel processes. We are doing individual versions of them. So there are many activities, but we are not there yet.
No.
I think there are lots of activities at the Twente as well, but.
Yeah, but is there anything that is special about these having discovered these mechanisms, that we should? What can we learn from it, and can we also use these kinds of mechanisms somewhere else?
For instance, what we did in our case is that once you know which receptor it is, we try to understand their working mechanism, and then we play with that mechanism to do different things. For instance, in the bacterial version, we can change it from mechanosensor into anything you like to sense and open. And what we did, for instance, we converted the mechanosensitive channel into a pH-sensitive channel by just playing with its working mechanism, and then put it into a container, like corona vaccine, you know, it is in an envelope. So we had that envelope and put the ion channel that would recognize the pH of how acidic the environment is. And we put a cancer drug into it and send it to animals with brain tumor. And what happens is that the whole thing goes there, and channel as a door recognize the acidity of the environment, which tumor cells are more acidic, tiny little bit more acidic, and now you can engineer that, and they open and release the drug, so then you wouldn't get side effects. Or you can think of making any sensors, because these molecules generate electrical signal. So if you engineer them to detect an analyte, for instance, in case of coronavirus, one of the molecules spike or so, and then as soon as it binds to the channel, it opens it and generates detectable signal. So with single molecule, you can use it as receptor and amplifier in a biosensor, for instance. Or you can also think of making beverages that feel cool, even though they are not in the refrigerator. So that's the simple one.
That is what Willy Wonka used, right?
Yeah, something
Exactly.
like that,
Yeah. Okay, now I understand that.
Yeah.
More questions? Yes, please. Please wait for the microphone.
This is a little bit more of a technical question, but for the second person who won the Nobel Prize, so Patapoutian, in his hypothesis, you mentioned something about transmembrane.
Yes.
Could you maybe explain it?
Because, transmembrane is, this is the room, and here is the cell, and the walls of this room are the membrane, and the door goes through the membrane, so it is transwall, and in that case it is transmembrane. So you are just, if this is the membrane, so, and then transmembrane is going through the membrane. So, because its structure is very different chemically, so there are some water-hating part, and your molecule receptor should stay there. So it also has a water-hating part as a belt, which fits it to the membrane or to the wall, like a cement. And then it stays there. But transmembrane means It is through the membrane, going through the membrane region. There are specific parts that it should be very hydrophobic, so then you can figure out.
Yes, thanks for the explanation.
You're very
Yes.
welcome.
Okay, are there more questions? Yes, in the back. Oh, there's two. First here, over behind the fence, and then we'll move to the gentleman in the green shirt.
I just had a question about the second one who won also the Nobel Prize, about sensing of pain. So you mentioned these sort of genes in the neurons that enable us to sense pain. Could that be something also for people who cannot sense pain, patients who don't sense pain? Can we introduce these genes to them, for example?
Yeah, I mean, if you know, when these experiments are done either isolated neurons or animals, and when it comes to human, we are all depend on genetics and identified mutants. Some people don't feel. Then most probably they have a trouble in these circuits, for sure. Then that is we learn by looking at the mutants to see, and they identified already multiple point mutations in these channels that people have different. They are very sensitive to pain, for instance, just the opposite of that. But and if you know how they work, so you can develop drugs to compensate the effect of mutation. So this is the goal in the medical part. How can you correct? Yeah.
Okay, thank you. Please.
So I've seen that some gel ointments for pain relief also have capsaicin in them. So is that like the mechanism? Is that something on the receptor level, or is that something on the neurological level? How does that work?
I don't know.
Oh, okay.
I will check it, but I don't know.
Sure.
Very
Yeah.
good question. All right.
Maybe it is so painful that you don't feel the real pain anymore. I don't
It's
know.
a distractor, yeah.
Yeah.
Yes. Maybe last question then here in the center.
Yeah, I was wondering, because there are definitely two different receptors for the cold and heat, how come that you sometimes experience hot things as cold and vice versa?
What do you mean?
That if you, if for example, experience extreme heat as cold, or cold as heat, or you never experienced that?
No, not yet. I don't know. It looks like more oversaturated, but I'm not sure. No.
I know that ice can give a burning sensation,
Burning
I guess, but
sensation, yeah.
that's maybe something different. I don't know. I'm not an expert.
I will check. It's a very good question.
Very good question.
But I don't know. Yeah.
Yeah. Something to think about. Well, thank you very much.
Thank you.
Thanks. Let's thank Professor Kocer once more for a wonderful explanation. And then we've arrived already at the last topic and last prize, Nobel Prize in chemistry. And the introduction will be given by Professor van Maarseveen from the University of Amsterdam. Professor van Maarseveen did his PhD in Nijmegen. And then after spending a little bit of time in industry, also moved to the University of Amsterdam, where he is now professor. And the professor was awarded to Benjamin List and David MacMillan in the area of chemical catalysis. Professor van Maarseveen, please, the floor is yours.
Thank you. Maar dat wil zeggen dat ik onmiddellijk nog trots ben om hier in Twents wat te vertellen. But I switched to English now. I was saying in the dialect, the local dialect here, that I was very proud here to tell a story about the Nobel Prize, because I was raised here in Enschede and then I left, unfortunately. But two guys that were in the football team that I was the worst football player ever. So when we were in the primary school, I was sitting there in the front, and I'm really proud to have them in the audience. And one of them is my brother-in-law, and I know him a lot longer than I know my wife. Okay, now let's start then with the topic. The topic of the Nobel Prize in chemistry was, as you can see, was on the development of asymmetric organocatalysis. And I think that's a whole lot of difficult words after each other. But first, do something practical. Why is it so important? I have here a bottle, 2 bottles I have, and there is limonene on it. And limonene, and one says minus limonene and the other says plus limonene. So they should be different. So what I will do is now an experiment. I'm a chemist, I'm doing experiments, of course. And then I have a very simple question. I hope that I can open it up. Yes, I can. Otherwise, I would go to Halme. He was always the strongest in school. And then my simple question to you is, when you smell these two bottles, do they smell the same or do they smell differently?
They smell the same.
You think that they smell the same? Now let's take another one, and I take, I take a young girl. The girls have far better noses than men have.
That's a lot of pressure.
It's a lot of pressure. Yes, I know. I realize.
Now I want to find the difference. I don't know if I'm impartial anymore.
It's a little difference. It's a little difference between these two. So the difference between these two compounds is that when you have a carbon atom, as I have here, and a carbon atom, it's surrounded by 4 different groups. And then, when that is the case, then these molecules, they can be mirror images. So the blue one is pointing towards me, and then the green one to the top. And as you can see, they are absolutely the same. They are the same molecules. They are superimposable. But as soon as I then just swap 2 of these substituents, then things change completely. So now the green one at the bottom, the blue one towards me. As you can see, these molecules are mirror images now, really mirror images. I can do what I want, but they are not superimposable. And that's the same with the 2 molecules that I have there that are called limonene. One is the mirror image of the other one. And our nose is able to discriminate between these 2 molecules. So that means that for our body, that are really 2 different molecules. And that is very, very related to nature. When we look at the molecules in our body, and especially the proteins, they are made of molecules which are mirror images. And in nature, only one mirror image exists, and not the other one. And that's really key. So these are simple molecules, but many drug molecules, they also are asymmetric. So also molecules that exist in 2 mirror images. And that went completely wrong at the end of the 50s, when there was a new medicine then for women who were suffering then from illnesses related to pregnancy, so nausea. And it turned out that when these children were born, so that was a new drug, and doctors, of course, then they want to have the most safe drug, especially to mothers who are pregnant. But that turned out to be a drama. All these children, they really were disabled, and the size of the limbs, everything was wrong. And that was because that molecule was administered as a mixture of the 2 mirror images. And from that time, chemistry changed completely. And chemists were looking for methods. How can we make only one of the mirror images of a molecule? Now, and that's really a very important aspect of the Nobel Prize in Chemistry of this year. Now, let's first look at the 2 guys, Benjamin List and David MacMillan. Both are born in 68, so they are 53 years old, and it's rather young for obtaining a Nobel Prize. And Benjamin List is a German. He was born in Berlin. And David MacMillan, he's a Scottish guy, but he's now also then affiliated to Princeton University. So there were 2 Nobel Prizes at Princeton this year. And Benjamin List is now working for a Max Planck Institute in Mülheim in Germany. Organocatalysis. An asymmetric organocatalysis. So asymmetric means you make only one mirror image. And organocatalysis means that you are doing the catalysis with just an organic molecule. And that means a molecule made up only by carbon, hydrogen, and then oxygen and nitrogen. But no metals involved. That's organocatalysis. Now, I already explained what happens when you have a molecule then with a tetrahedral carbon atom with 4 different substituents, that you have mirror images, and then we go to catalysis. So this is the Nobel Prize 20 years ago. So that Nobel Prize was catalytic asymmetric synthesis. So that's almost the same. Only organo came to it. So you think, why did they give 2 times the Nobel Prize to the same thing? That's a different story. So what you see here in this reaction, and this is a reaction which is invented by Barry Sharpless. What you see here is that this double bond is oxidized and 2 alcohol groups are introduced. And what you can see, this one is pointing to the front and the other one is pointing to the back. And that makes this molecule also an asymmetric molecule. But in this reaction, only one mirror image is formed. And the key element is osmium tetroxide, that's a metal. So this is a reaction, it's already known for decades, but only when you take osmium tetroxide, you get a mixture. You get a mixture where 50% is this alcohol to the top and that one to the bottom, and the other 50% is the other mirror image. And what Barry Sharpless invented is when you take this derivative of a natural molecule, quinine, then what happens is this metal then will then bind to this natural molecule, and also this is an asymmetric molecule, but only one mirror image, and then in the vicinity of this natural molecule, this metal then is able then to do this oxidation in an asymmetric way. Now that was the Nobel Prize in 2001. And then look at the definition of what a catalyst is. So that's around that time in 1996 in the book. This is really a classic and total synthesis. It's known by all the synthetic chemists. And there is the definition. In a catalytic asymmetric reaction, a small amount of an enantiomerically pure catalyst, either an enzyme, the natural catalyst, or a soluble transition metal complex. It's very difficult, but what it means is a metal, you need a metal for catalysis surrounded by something that's organic. But you need a metal, so or an enzyme or a metal, that's used then to produce an optically active compound. So only one mirror image. Okay, that was the definition. Now, and because of the Nobel Prize of this year, this definition is completely wrong. Because already people were thinking, all the catalysis at that time was all done with metals. And people were thinking, do we really need metals? And then when you go into nature and you look at enzymes, and enzymes are the natural catalysts. And then when you look at enzymes, what is the mechanism then? How is an enzyme catalyzing a reaction? And this landmark science paper in 1974, that was of scientists at that time from industry. At that time, industry really had laboratories where really high-end science was done. That's not anymore now in 2021. So at the Ross Institute of Molecular Biology, don't look at the details, these people have elucidated exactly how you start with a simple molecule and then how the enzyme then carries out that reaction to end up with a more complex molecule, but also then completely in an enantiomer selective fashion. So they elucidated that mechanism. And also there they pointed out, hey, it's catalysis what happens in the enzyme, and no metal is necessary. Now, and then a Dutch story. So there was, it's at the same time in Groningen, Hans Wijnberg and René Helder there. They have published for the first time that you can also use a small molecule, just a small molecule, to do a reaction. So this is the catalyst, you do a reaction and you get a product, and then you just got a little bit more of one of the mirror images as the other. It was not really 100% of one mirror image, but the beginning was there. So it also started in Groningen, and Hans Wijnberg, that was really a character. That was a character. So Hans, he's one of the few survivors of his family. Hans is Jewish, and Hans then, he went to the United States in the Second World War, and he was really an elite commando in the American forces. So dropped with a parachute behind the front lines. And Hans, he really was a character. I've known him quite well. But also the nice thing is, and now I changed a little bit, is that Hans is also the PhD father of Ben Veringa, who got the Nobel Prize 5 years ago. And as you can see then, this is a publication by Hans Wijnberg and René Helder. And René Helder was very important for Ben Veringa, our Nobel Prize winner, because when Ben was a student, then René Helder was a supervisor. And in Dutch here, René Helder said to Ben Veringa, you better stop with chemistry because you're so bad in the lab, you will never ever reach something. But it was a story that Ben Veringa told in Emmen, where he grew up, and he invited also there René Helder, because René Helder, of course, is a hero. Okay, but let's go back now, Now I come to the Nobel Prize winner, so Benjamin List, one of the two. So enzymes can do reactions then without metals. And then what they are doing at the Scripps Research Institute at La Jolla at that time was that they were able then to make antibodies that can catalyze a reaction. And an antibody, it's also a protein. So similar to an enzyme. And then what they did is they elucidated exactly how this antibody was able then to catalyze this reaction. So two components, you bring them together, you get a product. And as you can see, this is a carbon atom, there's also a hydrogen there. It has 4 different substituents. And then the two mirror images are formed in a ratio of 95.5 to 4.5. And that's really fantastic. And now comes the nice thing. So in the same institute, Benjamin List, together with Carlos Barbas, who unfortunately deceased 7 years ago, otherwise he would also be one of the Nobel Prize winners. So what they did is, they just took one of the amino acids out of the antibody, just one of the 20 proteogenic amino acids, proline. So a building block of a protein. So proline, that simple amino acid, was able to catalyze this simple reaction and gave then one of the enantiomers, one of the mirror images really in excess. That was the beginning of organocatalysis. And at the same time then, the other Nobel Prize winner then, MacMillan, he did the same reaction. Using a slightly other catalyst, not proline, a derivative of that, but it really happened at the same time. No, and then it went very fast. So this is the landmark Jack's paper then where List for the first time published this reaction. And there we also completely elucidated the reaction mechanism. And this is the catalyst. And this is the natural molecule proline. And then the chiral information, so the asymmetry of that molecule then, he nicely has shown in the reaction mechanism how the asymmetry of the original proline molecule is then finally translated into the product. So really a landmark paper. Now, what is the status now of this field? Thousands and thousands of publications further in 20 years' time when List published this for the first time. And also when it's already used in industry. So what you can see here is the synthesis of a drug. The name of it is Rasiles. And this drug was made then by using this as a catalyst. It's not proline, but this is somewhat of a derivative of proline. And that's also, many people in the world have made derivatives of these catalysts. But as you can see, the synthesis of this drug molecule, it's done now completely using organocatalysis. I will not go into the details of the synthesis, so no metals involved. And when you look in catalysis over the last 30, 40 years, a lot of catalysis was done with very precious metals, such as palladium and ruthenium and osmium. It's not so much around of that. And also these metals are very toxic. And now with organocatalysis then, we really can use now organic molecules which are far less toxic, and you easily can make them, and that makes the synthesis in the future a lot more sustainable. And so what they really did is, looking at nature, look how nature the catalysis does, and they take that mechanism out into a small molecule and use that then in synthesis, and it was really a game changer. So then, due to Benjamin List and David MacMillan, and now we as synthetic organic chemists, we really now have in our toolbox with a lot of reactions, and we really now have a new tool that's organocatalysis, and that we really use now, I would say, on a regular basis then, to make molecules who are there in mirror images, only to make one mirror image of a molecule. Thank you very much.
Questions? Yes, please. Just wait a minute for the microphone.
In the beginning of the talk, you mentioned that in the nature we just have one chirality of molecules,
yes.
If I understand correctly.
Yes.
Do we know what's the reason behind that?
It's a very good question. Maybe I can explain that a little bit. So when you look at a protein in our body, so the average size of a protein is about 250, 300 amino acids. So there are 20 amino acids as building blocks for proteins, 20. So imagine when you just make then a very small protein made up of 2 amino acids. Now then you already have 20 to the power 2 possibilities. And that really goes with an exponential. And the chirality of the molecule, so what I mean the handedness, also determines very much what the three-dimensional shape will be of that protein. And when nature would have used also the other enantiomer, that would mean that we would come to proteins of a really an undefined structure. So nature would not be able then to control really the three-dimensional structure of a protein. It would really be a chaos. So when you think about it, that life is built on, I would say, building blocks that only have one-handedness. To me, that's quite logical. Otherwise, it really would be chaotic. You could not control the three-dimensional structure of a large biomolecule. Although there are really some how do you call that? Exceptions. Yes, very good. Exceptions. One very important one is lactic acid. And so lactic acid, of course, that's the acid that you have in milk. But lactic acid is also what your muscles produce when you do too much sports, but then in a regime where there's no oxygen. But that lactic acid, what you get in your muscles, is really the mirror image of the lactic acid that you have in milk. Because our body also has enzymes that are able then to, of lactic acid specifically, to put one mirror image into the other. So go to the Lidl and buy the cheapest yogurt, you know, all that nonsense with a left-turning lactic acid, it's all nonsense. But that is really the exception. One of the few. And lemonade.
Very nice. Are there more questions? Yes, please. Wait for the microphone. All the way on the other end. You're developing some lactic acid now.
Yeah, from this reaction system, I can only imagine that because it catalyzes an organic reaction, so the catalyst and the organic compounds, the other organic compounds will be in a homogeneous system.
Mm-hmm.
So
yes.
Does it mean that it will give another problem in the separation for the catalyst and the compounds?
Yeah, the question here is when you do reactions, you have your starting materials, you put them together and you get a product. But now you have to add an additional catalyst. So at the end of the reaction, then you have your product and the catalyst. And how do you separate them from each other? Is that the question? Yeah, that really, so I've shown now only proline as an organocatalyst, and there are already hundreds and hundreds of different organocatalysts out, and it's really a very good question. And it depends on the type of catalyst, what kind of purification you use to separate really the catalyst then from your product. Hey, you don't want the catalyst in your product, but also you want to have the catalyst back to use it in another reaction. And there is no general method to separate these two, no general method. But in many cases, also when you look at proline and the other ones, then an organocatalyst can be a basic molecule, an organocatalyst can be an acidic molecule, and these properties, that really helps to separate them from your product by simple extraction, by taking then an organic solvent and an aqueous solvent, and when you choose the right pH of the aqueous solvent, and then you really can control the conditions that your catalyst goes into the aqueous layer and that the product that you want remains in the organic layer. So these things, there are absolutely solutions for that.
There's a question over here.
I have a very small question. On the previous slide, I saw in the last catalyst, I saw silicon.
Yes.
What is that?
Yeah, it's a very good question. Silicon, that's also so fascinating. Eh? When you look at the periodic table, there is carbon, and that's the element of life. And then when you look on Earth, how much carbon is there? When I ask the question, so in the Earth crust, how much carbon is there? So the weight percentage of carbon in the Earth crust. Who knows it? 1 or 2%. Who says less? Who says more?
Less.
It's 0.03%. It's almost nothing. It's almost nothing. But then when you look at silicon, silicon is one below in the periodic table. So that means that the characteristics of carbon and silicon should be quite similar. But it's absolutely not. So silicon, there's 27% in the Earth crust. So life has chosen for carbon, not for silicon. There are reasons for that. Silicon is really useless. But silicon is very useful here as an element, and that's because oxygen-silicon bonds are very easy to make. And the reason that this compound here is on silicon is it just has one function. So when you want to make one enantiomer, so one mirror image over the other, you have to discriminate one side of a molecule over the other. So you need something which is very large in a molecule. And what this group is doing is nothing else as just being large. And a silicon with 2 methyls and this very large T-butyl group, it's just a large group. And the silicon was chosen here simply because an oxygen-silicon bond is so easy to make. And we know that. What is a very famous compound which is made of silicon and oxygen? Sand. Yes, sand. It's silicon dioxide. It's carbon dioxide is in the atmosphere. But silicon dioxide is sand. And that's what I have seen from the first lecture, the second, and my one. It's all about molecules. It's all about molecules.
More questions? Yes, please.
I was wondering, maybe there is a room for a third Nobel Prize in this, that combines the organocatalytic with synthesis with catalytic synthesis, because there are some enzymes, they really need ions, magnesium and all that. I was wondering if anybody used to combine organocatalytic synthesis with metal ions?
Oh, absolutely.
Depends on the reaction, of course.
Absolutely, absolutely. And that's a very new field now, a very new field, where organocatalysis is then combined with ruthenium, mostly as a metal, and because ruthenium is a metal that's really able, when you shine light on it, then ruthenium is able then to extract electrons from a molecule, so to make radicals. So then you use light essentially to activate another molecule. And light is a very, very sustainable reagent, because light, it's all abundant. And look at nature, how nature does synthesis. Nature is doing synthesis and gets the energy from light. So this is also something we are copying, so that we use light. But then mostly now we need metals to do that. Ruthenium is a very important one. But also other groups now are going away from these metals and also are looking for purely organic alternatives.
Thank you.
Photocatalysis is the name.
Okay. Are we copying nature in terms of the handedness? Do we choose the same right-handed or left-handedness? Or?
It's also a very good question. Nature can only make one mirror image.
Yes.
And that's also a drawback from nature. As sometimes when you have a catalyst and you take it from nature, you only have that mirror image. But sometimes we need a molecule that should have the other mirror image. And then you need the mirror image of your catalyst. And that can be problematic to make it.
Okay.
Yeah.
Okay.
Proline is a simple one, but other complex organic catalysts, they are more difficult.
So it's not so
but
trivial.
we steal always the stereo information. We steal it from nature. It's always what we do. There it comes from.
Okay. 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 I think it's 7:30. That brings us to the end. Let's thank Professor van Maarseveen once more. And I would like to also give one more hand to all the speakers of tonight for a wonderful lecture. And I would like to thank you. But before we leave, I would like to thank the team of Studium Generale who made all this possible. The people who you see behind the cameras in the back. Peter Timmerman, thank you very much for helping and organizing. Also on behalf of the faculty again and of the university. Thank you for your attention and see you next year.
And I want a big hand for Gert-Jan, who organized this session together with us, and you moderated it excellently. So thank you very much. See you next year.